Just look around you. The phone in your hand, the laptop on your desk, even your coffee maker, there's this invisible magic happening inside all of it. Today, we're going to pull back the curtain on that magic, on the tiny, brilliant brains that run our entire world. So, have you ever really thought about it? What is the secret ingredient that makes all of our modern tech, well, work? The answer is a special class of materials called semiconductors. These little guys are the reason we went from computers the size of a room to devices we can literally wear on our wrist. But before these tiny powerhouses showed up, electronics looked a whole lot different. Before semiconductors, we had to rely on these things called vacuum tubes. And trust me, they were clunky. They were big glass bulbs, super fragile, they guzzled power like crazy, and they burned out all the time. Then semiconductors came on the scene and just completely changed the game. They're tiny, tough, sip power, last forever, and run on way lower voltages. It was a flat-out revolution. And to understand why, we've got to zoom way, way in, down to the atomic level. To really get what makes a semiconductor so special, we first need to talk about how any material decides whether to let electricity flow or not. And it all boils down to a fundamental idea in physics called the energy gap. You can think of it as the rule book that tells electrons how they're allowed to move around inside a material. Okay, imagine two highways for electrons. The first one is the valence band. This is like a packed, bumper-to-bumper city street. The electrons here are stuck, basically tied to their home atoms. The other highway is the conduction band. This is the wide-open autobahn where electrons can zoom around freely and create an electrical current. The space between these two highways, well, that's the whole secret. So at one extreme, you have insulators. Think rubber or glass. For them, the energy gap is massive. It's like the autobahn is on top of a giant cliff with no on-ramp. It takes a ridiculous amount of energy for an electron to make that leap. Then you have the other extreme, conductors, like copper wire. For them, the two bands actually overlap. There's no gap at all. It's like the city street merges right onto the autobahn. Electrons can just cruise over whenever they want. Easy. And this, right here, is where semiconductors, like silicon, come into the picture. They are the just right material. The energy gap isn't huge, but it's not zero either. It's this perfect, manageable little gap. It's small enough that we can give electrons just a little nudge, say with a bit of heat or a small voltage, and get them to hop over into that conduction band. And that ability to control when it conducts and when it doesn't, that's its superpower. So, it's all about control. But how do we get even more precise control? Well, we use this really clever trick called doping. Seriously, think of it like being a chef and adding just a tiny pinch of a secret spice to a recipe to completely change its flavor. All right, first up is something called N-type doping. So pure silicon has 4 outer electrons it uses to link up with its neighbors. Now, what if we sneak in a tiny amount of an element that has 5 outer electrons, like phosphorus? 4 of those electrons will form bonds just like the silicon, but that 5th one, it's just left over. It's an extra free electron just hanging out, ready to be kicked into the conduction band at a moment's notice. And since electrons are negatively charged, we call this an N-type semiconductor. Makes sense, right? Now you can probably guess what's next. What if we do the exact opposite? With P-type doping, we add an impurity that only has 3 outer electrons, like aluminum. When it tries to bond with its 4 silicon neighbors, it's short 1 electron. This creates an empty spot, a vacancy, that physicists cleverly call a hole. And this hole acts just like a positive charge because it's so eager to grab an electron from its neighbor. The movement of these holes from atom to atom is just as good as a current. Okay, so let's recap real quick. We've basically created 2 custom flavors of semiconductor. We've got N-type, which has extra negative electrons ready to go because we added a donor, and we've got P-type, which has extra positive holes ready to be filled because we added an acceptor. This is where it all starts to get really, really interesting. So, what happens if you take a piece of N-type material and stick it right next to a piece of P-type material? You create something amazing, a p-n junction. And that is the absolute core of a component called a diode. Simply put, a diode is an electronic one-way street for electricity. The very instant these two materials touch, a little bit of chaos breaks out. All those extra electrons on the N side see the empty holes on the P side, and they just rush right over to fill them in. But this leaves a little zone right at the border that's now empty. The electrons that left are gone, and the holes they filled are gone. It's been depleted of any free carriers. So, let's walk through that one more time. Step 1, we join the materials. Step 2, electrons and holes immediately start crossing that border. Step 3, this movement creates that empty depletion region. And finally, step 4, that empty region creates its own little electric field, like a barrier that pushes back and stops any more electrons from crossing. The system finds its own equilibrium, just waiting for us to take control. So, how do we take control? Easy. We apply a voltage. If we apply it in one direction, what we call forward bias, we essentially push against that built-in barrier, shrinking the depletion region and letting current flow right through. But if we flip the voltage around, reverse bias, we actually help the barrier, making that depletion region even wider and blocking almost all current. It's a perfect electronic gate. Open one way, close the other. Now, why would you want a one-way gate for electricity? Well, think about the power coming from the outlet in your wall. That's alternating current, AC. It flows back and forth. But basically, all of your gadgets, your phone, your laptop, they need direct current, DC, which flows in just one direction. A diode acts as a rectifier. It lets the forward-flowing part of the AC wave pass through and chops off the backward-flowing part. It's the very first, absolutely crucial step in powering almost every device you own. Okay, so a diode is a one-way gate. But what if we made a semiconductor sandwich? What if we put 3 layers together? Well, then you get what might just be the most important invention of the 20th century, the transistor. This little thing is the engine of the entire digital age. At its heart, a transistor is just 2 diodes stuck back to back. So you get an NPN or a PNP sandwich. It has 3 connections. And the core idea is absolutely brilliant. A tiny, tiny current applied to that middle layer, the base, can control a much, much larger current flowing through the other 2 layers. It's like using your pinky finger to open and close a massive dam. And that one simple principle gives the transistor 2 incredible superpowers. First, because a tiny input controls a huge output, it can be an amplifier. It can take a weak little signal and make it way, way stronger. And second, it can be an unbelievably fast electronic switch, turning that big current all the way on or all the way off just by tickling the base. Now, don't let this graph scare you. It actually tells the whole story perfectly. See that sloped part in the middle, the active region? That's amplification. A small change on the input results in a big proportional change on the output. But look at the flat parts at the bottom and top. That's the switch. It's either fully off in the cutoff region or it's fully on in the saturation region. Amplifier or switch, all in one. And it's that switching ability that truly, truly changed the world. Because what is digital information? It's just a long string of ones and zeros. A transistor that's on can be a 1. A transistor that's off can be a 0. You put billions of these microscopic switches on a single chip, flipping on and off millions of times a second, and suddenly you can do math, store memories, you can build a computer. So, let's just step back and look at the path we took. It's so logical. We started with the basic physics of a material, that energy gap. Then we learned how to hack it, how to dope it, to give it the properties we want. We used that to build a simple one-way gate, the diode. And then we layered them to create the master switch and amplifier, the transistor. From sand to silicone brains. Which leaves us with this final, kind of mind-blowing thought. We've just understood the fundamental switch, but the processor in your phone has billions of them. Billions. And the entire tech industry is in a constant race to make them even smaller, even faster, and pack even more of them into the same space. What does that even mean for the future? What new revolutions will the next generation of these tiny little switches unlock for us?